Let's have a look now at scientific notation. And you may have seen this before, but it's good to have a recap on this. So scientific notation really is a way of expressing very large or very small numbers conveniently. Let's take an example. So let's say 52 with 16 zeros, 4, 8, 12, 16 zeros. Okay, very large number. Rather than writing it like that, this could be, for example, the distance, from here to say a nearby star in kilometers, for example, or it could be the number of atoms, for example, that makes up an object. Rather than writing it with all these, for example, all these zeros, we could write it as 5.2 times 10 to the 17. So this may be familiar to you, may not be, or you might have forgotten. So it's a good recap, nevertheless. How about say really small numbers, for example? So if you take, for example, 0. A whole lot of zeros, 135 meters. Well, we could express that as 1.35 times 10 to the negative 16. So this negative index, okay, this negative index just means that it's a very, very small number. In other words, it's a decimal, a very small decimal. Okay. So scientific notation. Okay, so I'm just going to adjust the camera a little bit just so you can see the bottom of the board. Okay, scientific notation has the form m times 10 to the power of n. Okay, where m is a number between 1 and 10, exclusive, so it does not include 1, does not include 10. If it was 1, then anything multiplied by 1 is just whatever it is, whatever you started off with. So 1's irrelevant, and 10, if you are multiplying it by 10, then the index actually could be brought into the 10 to the power of n by increasing the index. So 1 and 10 we don't include. N needs to be an integer. Okay, let's have a look at some examples. Okay, so first one, part A, write each number in scientific notation. Okay, so we have 151 million. That number looks somewhat familiar. That's roughly the distance in kilometers from the Earth to the Sun. Okay, so that's probably a small enough number to express in sort of normal decimal form. But for the exercise, let's express this in scientific notation. So the way we start off is we write it as 1.51. Okay, remember that's the m. Okay, so that's that there. Okay, so that's the m multiplied by, and it's always times 10 to the power of something. So we need to find out what that something is. Well, how we work that out manually, okay? In fact, if you just count the number of digits there are, not including the 1, but just up to the second, basically up to the second digit. So from the last digit to the second digit, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Another way you can do that is you pretend there's a decimal point, okay, at the end, and there kind of is one there, an implied decimal point. If you move the decimal point so that it's between the 1 and the 5, 1, 2, 3, 4, 5, 6, 7, 8. Okay, the number of decimal places that you move it to the left, that's the index of that you use to raise the base 10 by. And the reason for that is that when you move the decimal point, what happens to this number? In fact, you've turned 151 million into 1.51. So that doesn't make sense. It still has to be 151 million somehow. So all you're doing is expressing the same number, but just in a different form. Okay, that just really means, well, times times 100 million. Okay, let's have a look at part 2. 0 point, a whole lot of zeros, 0.12. Okay. Converting this into scientific notation, okay, I know that the m is going to be 1.2 times 10 to the power of something. We need to work out what that something is. Let's move the decimal point now to the right-hand side. And in doing so, what you're doing is that you're making the number bigger by a factor of 10 each time. But then we need to undo that by raising it to the power of some negative. Okay, let's count the decimal places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That number looks somewhat familiar as well. That number is in fact the diameter of a hydrogen atom in meters. Okay, so you could look that up for yourself, but it's roughly 1.2 times 10 to the power of negative 10 meters in diameter, one hydrogen atom. Okay, Let's have a look at part B. Okay, so part B links in significant figures with scientific notation. So we're going to write 384,400,000 in scientific notation, correct to two significant figures. Okay, so it says two significant figures first. So we could either do it one of two ways. Either we could write it in scientific notation first, and actually, why don't we just do that? So that's 3.844 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the power of 8. Okay, and then we're going to round that to two significant figures. Okay, so we've got the 3, that's the first significant figure, and then we've got the 8 is the next significant figure. That's going to be 3.8. We don't have to round the 8 because the number next to the 8 is a 4. 8 stays as 8 times 10 to the power of 8. Where does this number come from? You might want to look up the distance, or roughly the distance of the Earth to the Moon in meters. Okay, so it's roughly thereabouts 384,400 thereabouts kilometers, depending on where you measure the distance from. But some nice numbers there. Okay, last one, part C. Write each number in normal decimal form. So now we're just going back again to to regular numbers without using the times 10 to the power of. Okay, so what we can do, okay, is to write down 1.65. Okay, so a bit of a shortcut here. Put some zeros in. Okay, you can put as many zeros as you like. Just fill it up with some zeros. There's going to be maybe 8, sort of a few zeros there, probably 7 or 8 zeros. Then what we're going to do is we're going to move the decimal point to the right-hand side. We're going to move it 8 places. So we're going to go back. We're going to basically undo part 1 here. So the opposite of part 1. Okay, or part A, sorry. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, these zeros are not needed. So the number would be 1, 6, 5, and 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6 zeros. Okay. Right. Likewise with 1.5 times 10 to the negative 7. We know that's going to be a decimal because of this negative sign here. Okay, it's a negative number. So sorry, it's a negative number index, but it means that it's going to be a very, very tiny decimal. Okay, so what we're going to do is we're going to, it's going to be 1.15, so 1.5, but I'm going to put some zeros before it, like that. Okay, what we're going to do is we're going to move the decimal point back 7 places. 1, 2, 3, 4, 5, 6, 7. Okay, does that work? Let's have a look. Okay, if we were to go back and reverse it, we don't need those decimals there. Sorry, the zeros there before the decimal point. So that's just 0.00. I have 1, 2, 3, 4, 5, 6 zeros. 1, 5. Okay, just to make sure that it does work. If we had to move the decimal place 7 places back to the right again. 1, 2, 3, 4, 5, 6, 7. Yes, it does work. So I'm satisfied that that is in fact the correct answer. Now, in the next video, we can use another mode on the calculator. Just quickly, it just came to mind. Let's say you wanted to check your answer. Let's say you wanted to check this answer here. Okay, so hopefully you can see that okay. Because that was one thing I didn't put into this video right up until the very end, so apologies for that. Let's enter in this number here into the calculator. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we've got that there. Okay, putting that into basically into scientific notation. A couple of ways we can do that. There is actually a mode that we can use, which is this mode here called SCI. Okay, so then asks you the number of significant figures. So I'm going to use 2 significant figures, and it's 1.5 times 10 to the negative 7. So in fact, it is the correct answer. Okay, I'll do another video on this mode because it is actually very useful. The only thing you've got to watch out for is make sure you bring it back out of that mode by putting it into this thing called norm, mode norm and number 2. Okay, but I'll talk about that in the next video.